Hi, everyone, and welcome. My name is Felix Knight, and I'm the Technical Director at Lightware UK, and I'll be your host for this event. Today's webinar is called Behind the Scenes of DVI, HDMI, and DisplayPort, Part 1. Over the next 2 hours, I'm going to talk about the basics of digital video, DVI and TMDS, EDID and EDID management, and we'll also give an overview of HDMI technology. I'm going to share my presentation, and you're also going to see me through my webcam. Depending on what type of device you're using, you can either see two feeds next to each other or on top of each other, and you can manually resize windows to make one bigger and vice versa. If you're watching on a smartphone, then you can swipe left and right between the camera and the shared screen. By default, all the attendees are muted, but questions can be submitted at any time during the webinar using the chat box. So please use the question box. And we will answer as many of them as we can at the end. So yeah, please submit questions as we go along. So without any further ado, let's continue with the training. So let's start with the basics of video signals. So video is basically a kind of trick. There's lots of different tricks and facets of how our eyes work in the reproduction of video. And the first and most basic one is if we get enough still images and we display them in sequence, refreshing them at a certain speed, then our eyes process that as a moving image. So within digital video or video of any kind, there are various things which define the video or the viewing experience. The first is resolution. So hopefully most of you are familiar with this. This is how many pixels there are on the screen. So we always want to have a lot of pixels on the screen so that we go to beyond the point where we're actually able to tell them apart. The second is the frame rate. So this is how many frames we are displaying in a given period per second normally. And in order to create this illusion of video or moving image, we need to display enough of them quickly, so have a high refresh rate. The third is dynamic range. So dynamic range is the level between the darkest black and the brightest part of the image. So the range between those 2 points, the black level and the luminance. We also have the color gamut, which is the chromaticity of the images. And then the fifth one here is the color depth, which means how many different shades of the same color can we display, or how close can two neighboring colors be in the chromaticity. So as I mentioned, with our video, we have our individual frames, our still images that we project one after another. And if we look closer at those still frames, we'll see that they're made up of pixels. And within those pixels, we have red, green, and blue subpixels. So this is another trick of the video display or viewing a video, is that within our eyes, we have 3 different types of cells that can sense color. One is sensitive to red, one is sensitive to green, and one is sensitive to blue. So using these 3 color components, and by pulsing them in different intensities, we can actually recreate all of the colors that we can see with our eyes. So there's no need for a display to emit all the possible wavelengths that our eyes can process. It's actually enough just to have these 3 subcomponents. So let's take a bit more of a detailed look at some of the things we showed already. So going back to resolution, the number of pixels we have on the screen. We have different terminology to indicate the amount of pixels. Sometimes we say megapixels, or we say the vertical and horizontal sizes, or sometimes they have their own name like Full HD, VGA. So nowadays, Full HD or 1920 by 1080, also 2 megapixels, is something of is the most widely used standard. But we also have, as we'll see tomorrow, 4K displays, and now some display manufacturers have even started to reduce 8K. So there's a trend to stick more pixels on the display and keep pushing the resolution higher and higher. The second parameter is refresh rate. So how many frames we display within 1 second. So it's a frequency in hertz. Typically, to the minimum frame rate to achieve the illusion of a moving image is around 20 frames per second, so 20 hertz. A lot of cinema is done in 24 hertz. Most monitors and displays are doing 50, 60 hertz, but now, you know, with 3D applications, you might go to 120, and we've even done some stuff with the sort of professional live gaming environment where you need to handle 240 or even now 360 hertz signals in the latest gaming monitors. Going on to color depth, this tells us how many colors we can choose from. And the first generation screens had only 2 colors, which was black and white, or it was actually green and black in the very beginning. Then we moved to grayscale screens and colored screens with 8-bit color or 16 color, 256 colors, and so on. Nowadays, the average number is in the magnitude of millions or even billions. The fourth parameter we have was the color space. To put it simply, each color space defines 3 points within this CIE color diagram to make up a triangle. So the CIE color diagram represents every color that the human eye can process, and we pick 3 points to take a section out of that. And so as we developed newer and newer standards, we take a larger and larger section of this diagram, and we can represent more colors. So as I mentioned, we have the red, green, and blue color information. If we want to transport this information from a source to a display device, then we need to use some kind of video interface. And we can choose from a lot of different interfaces. There are the analog interfaces. So these are typically legacy technologies like composite video, component video, S-video, VGA. And these are analog signals, so they use a range of different voltages to encode the color information, continuous range. And then we have the digital technologies like DVI, SDI, HDMI, and DisplayPort. We also have HDBase-T here. And these are using a digital binary system to encode the information. We're not going to talk so much about the analog interfaces because they're used less and less, but we'll be over the course of the 3 parts, be covering DVI, HDMI, DisplayPort, and HDBase-T. At Lightware, we don't make too many SDI products. SDI is a very widely used standard in the broadcast industry. It has a lot of benefits in terms of the transmission medium. You only need a basic coax cable. But in the world of Lightware and the type of products we make, we focus on DVI, HDMI, and DisplayPort. So, moving on, let's start talking about DVI. It stands for Digital Video Interface, and I'm sure most of you will know that this is what the connector looks like. DVI was introduced in 1999 and basically superseded the VGA standard. So if we take a look at the pins and look at what they're used for, so the most important are these 3 differential wire pairs to carry the red, green, and blue color information. And we also have another wire pair for the pixel clock. And these 4 wire pairs are the 4 TMDS lanes, which we'll talk about in a moment. With these 4 wire pairs, the maximum resolution you could send is in the DVI format is 1920 by 1200 at 60 Hertz. However, within the DVI standard, they introduced or they designed another 3 wire pairs, which can also carry red, green, and blue information. So when you're using all 6 wire pairs, then we'll be using dual link DVI, as it's called. And the maximum resolution with a dual link DVI, you could do 1920 by 1200 at 120 Hertz. So for a long time, this was the only way you could do proper 3D with digital video. Or if you go to 60 Hertz, you can increase the resolution to 2560 by 1600. Then we also have some ground pins, and then the DDC, the display data channel, which is a very important bidirectional low-speed communication channel, which handles communication between the sink and the source device, and we'll see what that does later on. We have the plus 5 volt and the hot plug. These are physical electrical signals that indicate whether the source is connected or whether the display is connected. So they're part of a physical handshake. And then the rest of these pins are used for analog signals. So if you have a VGA to DVI adapter cable, your VGA signal is basically coming across these pins. So if we look at our DVI display and we think about what's going through the cable when we transmit the signal, well, we can see the active video area, but this isn't the only thing that's going through the cable. If we remove the display, we can see that we have a second part of the image, which is the blanking interval. So the blanking interval is not something you see. The display cuts this area off. It exists for historical reasons because of CRT monitors. So back when DVI was introduced in 1999, there were a lot of CRT desktop monitors being used, and a CRT monitor uses an electron gun, and it fires electrons at the display, which is covered in a phosphorescent material, and those electrons cause that part of the display to light up. And effectively, what happens is the electron beam starts in the top corner of the image, and it paints along and gets to the end of the active area, and it needs time for the electron beam to turn off, come back to the beginning of the new line, and turn on again. Otherwise, it would just zigzag across the whole image, and you wouldn't see your image. So this is the reason why this is included in the DVI signal. But we're not working with electron beams anymore, so the blanking interval is not really totally necessary in most DVI signals. As you can see, it's not completely empty. We have the control data for the vertical and horizontal sync. So the vertical sync is when you reach the end of the frame to go back and start a new frame. The horizontal sync is when you reach the end of the line and go to start a new line. So the horizontal sync is happening thousands of times a second, and as we talked about earlier with vertical sync and refresh rate, that's 50, 60, maybe 120 times a second. With DVI, it's important to note that the active video area can only be encoded in RGB, so no other color space is allowed. And we'll take a look at some of the other ones they introduced later on with HDMI. So the pixel clock frequency is probably the most important parameter of a digital video signal, particularly with DVI and HDMI. It effectively tells you the frequency at which a pixel is being refreshed in the whole frame. So to calculate it, we take the total number of columns, the total number of lines, and we multiply them all by the refresh rate. So the key here is we're not just taking the active video area, but we're taking the total number of columns and lines from the full image, from the blanking interval as well. So in this example, which is a 1920 by 1080 active video area, the full columns is 2200 and the full lines is 1125. So columns is the horizontal and the lines are the vertical when we talk about video frames. And then we times that by the frame rate, which is 60. And if we do all that, we'll get 148,500,000. But we can translate that into 148.5 megahertz, so mega being million. So that means within 1 second, 148 million pixels are getting new information being refreshed. So if we take our pixel clock frequency, we can also calculate the data rate. So we know that we've got 148.5 million pixels are being refreshed every second. And so for each color component, each subpixel, that's 10 bits of new data. So if we times that by 10, we get 1.485 gigabits per color. And we've got 3 color components, so we times that by 3 and we get the total data rate. And yeah, we'll look in a minute at why we need 10 bits per pixel. Hopefully that's all clear, and yeah, if you have any questions at any stage, feel free to put that in. This is a screenshot of a Lightware feature called the frame detector. So in a lot of Lightware devices, we can actually measure the active video area, the blanking interval, give you all of the detailed signal timings, and even the pixel and TMDS clock. So this is a sort of Lightware diagnostic tool that can help you diagnose problems sometimes if you've got unstable video signals. If you see the values in this tool dancing around a lot, then you know you might have a problem. And it's also helpful to check physically, you know, what the resolution you think you're sending is actually being measured at with this tool. So if we talk about digital video representation, on the left, you can see our pixels again. And if we look next to it, we can see a magnified image of the pixels showing the red, green, and blue subpixels. So if we want to transform the video information into a digital signal, with digital, we're using a binary format with ones and zeros. So DVI uses 24 bits per pixels, which is 8 bits per color component. And with those 8 bits, you can have up to 256 different levels of each color component. So that's from full black to full red, same for green and blue. So if we have these 3 components each at 8 bits, that means in total, to get the total number of different colors we can represent, we've got 256 cubed, or 256 times 256 times 256, which gives us 16.7 million different colors, which may sound like a lot, but as we go through the behind the scene training, at various points you'll come up and see the limitations of this. So we're talking about 8 bits per color component, but when we did our calculation just then, we were timesing each color component by 10. So why is that? That's because when we are sending the video signal, we need to use an encoding format. So here on the left, we can see our binary representation with ones and zeros and the clock signal. We can turn that into an electrical representation where a 1 is represented by a high voltage and a 0 is represented by a low voltage. However, if we took this this signal and tried to send it through a cable, we wouldn't get more than 4 or 5 meters. The reason for this is because we haven't minimized the number of transitions. So every time that there is a transition between a low voltage and a high voltage, or a high voltage and a low voltage, we emit electromagnetic noise into the environment. And in terms of transmitting signals, we want to minimize that noise. If we just have a steady high voltage or a steady low voltage, we don't actually emit that much noise. It's the change between the voltage levels that actually causes it. So to get around this, the people who came up with the DVI standard decided to use an encoding process called TMDS, Transition Minimized Differential Signaling. And the first bit, the transition minimization, to do that, we use an encoding process, and we basically add on 2 extra bits to the 8-bit color information, and that's those 2 bits are used to encode, and then at the other end decode the symbol to give us the original data. So that's why we were using a multiplier of 10 on our pixel clock frequency. So as I mentioned, when we have transitions, this is where we emit electromagnetic noise into the environment. And with transmitting signals, we want to have the lowest noise, or we want to have a good signal to noise ratio. So we want to really minimize as much noise as possible. So if we're looking at this bit sequence here, this is the worst case scenario. It has 7 transitions. It's 1 0 1 0 1 0. So what we would do with that is we take this color data and perform our encoding. And now you can see we've only got 4 transitions from the original 7. At this point, the bit sequence doesn't represent, you can't say it represents the color information, it's a symbol. It's information of a different kind, let's say. So how does the transition minimizing work? Let's take this worst case signal with 7 transitions. The first step is the source will use the XOR or XNOR logic operation on all of these bits, and it will then count the transitions. So in this example, with XOR we have 4 transitions, and with XNOR we have 5 transitions. And because 4 is the optimum, that's less transitions, the extra bit, the 9th bit that is added on at the end, is a 1. So that allows the display device to know when it receives this symbol, this has been encoded using XOR, so I need to decode it and using the proper process to get back to the original. Then the second step is it will invert the signal. And so in this case, inverting it minimizes the number of transitions, or creates less transitions than not inverting it. And for the 10th bit, a 0 represents don't invert, and a 1 represents invert. So in this example, we've gone with XOR, and we've inverted the signal, and that's how we turn the 7 transitions down into 4. What is that? 5. 1, 2, 3. Yeah. So the key is that we're adding on these 2 extra bits for encoding, and it's an absolutely necessary part of transmitting the signal. So we've covered the transition minimizing part of TMDS. Let's look at the differential signaling part. In a digital system, voltage levels represent high and low logical levels, but voltages are always compared to a reference level, usually ground or 0 volts. And there's always a threshold for high and for low voltage. You can see that with these sort of gray areas. When the voltage level is in the gray area, it is considered, in the high area, it's considered high. When it's in a low area, it's considered low. So this is what we call a single-ended signal, where the voltage is compared to the ground level. Now, if we send the signal through a wire, the monitor receives this signal and tries to determine the logical values by periodically taking samples from the voltage. The wires have resistance, so they attenuate or weaken the signal, which means that the voltage will be lower. The monitor has threshold levels, but of course it takes attenuation into account, and so that's why the high voltage area is much thicker in the display. And if there wasn't any noise, this would be fine. But unfortunately, there's always noise, which means the voltage is randomly pushed lower or higher, and there are under and overshoots. If you look at this spike, you can see the problem of the single-ended signal. This voltage can either be considered a 0 or a 1, and so that presents the problem. That means we have to use a shorter cable which attenuates the signal less, or eliminate the noise. And so with a single-ended signal, you won't be able to send your signal very far. Differential signaling uses 2 wires, but it's not using the ground as voltage reference. It takes the original signal and then sends it through the other wire pairs, sends it through one wire pair, then it takes the inverted signal and sends it through the other one. So the inverted means that whenever the original signal is a high voltage, the inverted signal will be a low voltage on the other eye, and vice versa. And what we do is we twist these 2 wires together in a twisted pair. So if we send this signal through to the monitor doesn't use the ground level as reference. It only looks at the difference between the voltage levels in the 2 wires. Why is this better? It's better because the noise affects the wires in the same way, and they'll push the voltages in the same direction because we've twisted them together. This means that the voltage difference in the wires always stays the same regardless of the noise. So this allows us to transmit the signal much higher distances. The same idea being used here is used in balanced audio. So if you're familiar with that, you can get an understanding of this. So we've talked about TMDS, and as I mentioned before, we have the 4 TMDS wire pairs. So 3 of them carry the red, green, and blue color information, and 1 carries the pixel clock. So if we take our source and the graphics chip, and we have our original transition minimized signal, we turn it into a TMDS signal to send it through the wires. When we get that signal at the monitor, we still might have some problems. So the signal is attenuated. It has jitter, intra-pair skew, and inter-pair skew, and we have to fix these problems. A lot of these issues are factored into the design of DVI cables. They were particularly relevant when we were sending video signals over cadex cables using basic transmission technologies. HDBase-T solved a lot of those problems. However, we're seeing these problems occur again with HDMI 2.0 devices, and what you will notice with a lot of these problems is they increase when we increase the pixel clock frequency. A lot of them increase exponentially. So as we've gone to higher and higher pixel clock frequencies with HDMI 2.0, a lot of these problems are becoming more relevant. You know, despite having solutions for them in the past, they are they're sort of facts with physics. You know, they're sort of baked into the technology, and there's no way we can ignore them. So the first problem is attenuation. So the wires are made of copper, which is not a perfect conductor, so it has resistance and capacitance. The DVI standard defines a 1 volt total amplitude, and if we send this through a cable at the other side, we will have a much lower amplitude. With Lightware devices, some of our input ports have 40 dB attenuation, which is 1 to 100. So even with this 10 millivolt amplitude, we would be able to recover the original signal. But your average monitor doesn't have that much. It's usually 10 or 12 dB for a maximum of maybe, let's say, 10 or 15 meter cable going into the display input port. So what does attenuation depend on? The length of the cable. So a longer cable means more attenuation. The diameter of the wires. So a thicker cable means less attenuation, going back to the basic physics. And then, as I mentioned, with the frequency, the pixel clock frequency, the higher the pixel clock frequency, the higher the attenuation. If you imagine increasing the frequency and having to swing all the way between the high voltage and the low voltage faster and faster and faster, you can imagine how that might increase the attenuation, giving you less time to get to the highs and the lows. So this is what attenuation usually looks like on the screen. You can see these flashing pixels of different colors. Can be red, can be green, can be blue. What can you do when you see this? The first option, the easiest one, would be to decrease the frequency. So use a lower resolution or lower the refresh rate. You can also decrease the frequency by using a reduced blanking signal. So you can use a signal timing that reduces the blanking interval, so you're sending less through the cable and thereby decrease the pixel clock frequency. However, lowering the resolution and refresh rate might not be acceptable solutions for what you're trying to do. And what if you're already using a reduced blanking signal anyway? Those might be problems you can't get around. Another option would be to use thicker cables, or even use a shorter cable and a more optimal cable path. However, maybe in the system you're working with, everything's already installed. The customer has a hard requirement for the resolution and refresh rate that you have to use. What can you do then? Well, you can use a technology called equalization. So what is equalization? On the left, you can see our square original signal. And then on the right, you can see the attenuated version of it. So the first thing we need to do is amplify the signal. However, when we amplify it, we're not just amplifying the original signal, we've amplified the noise as well. You can see here we have the overshoots and undershoots. So we need to get rid of these. And so the equalization circuits will cut these out, cut the overshoots and undershoots out, and then we have the original noise-free square wave. And so this is what the EQ chips are doing. Going on to another issue that we see, so crosstalk between wire pairs. It's important to know that every conducting material can act as an antenna. Even your body acts as an antenna because it's mostly made up of conducting materials. If I attach an oscilloscope to your body, I'll be able to measure a very low amplitude, 50 or 60 hertz sine wave signal. And that's because the alternating current, the AC in all of the mains electricity wires going around your building would be emitting that noise, and your body effectively picks it up. The same thing happens in cables. If you run two wire pairs next to each other in a cable and they're carrying electronic signals, they will talk to each other. The red wire pair will affect the green wire pair and vice versa. So this is where these transitions that we were talking about earlier, the noise that they emit, that noise can get picked up by other conducting materials. So if we have these signals in the source and we send them through the cable at the top, once we send them through the cable, we'll get the result at the bottom. And you can see that where we have the transitions on the one wire pair, we're creating noise in the other wire pair. So what can we do to avoid this? Ultimately, the solution is to use shielded cables. So you want the wire pairs to be shielded from each other. In a DVI and HDMI cable, that's how they're designed. They're standard for this. So once you wrap the cable in something like aluminum foil or a suitable shielding material, the noise won't get through to the cable inside. Moving on to intra-pair skew. Intra-pair skew is an issue because even with the best equipment in the world, it's basically physically impossible to create two wires that are exactly the same length. There's always going to be some level of difference. You can use more expensive manufacturing techniques and machinery to get that tolerance to be closer and closer and closer, but ultimately there is a limit, and depending on the quality control and the price of the cable you're using, that can be a big difference. We actually had a case a long time ago where a customer in Norway was using a 20-meter Cat6 cable, and they couldn't even pass basic VGA extenders. So we did some troubleshooting, and it wasn't going anywhere. Eventually, we asked the customer to send us one of the cables, and when we cut it open, we actually saw something like you can see on the screen here. It was actually one straight cable, and then the other cable was just wrapped around it. And so you can imagine that over a decent sort of 5-10 meter distance, that's going to create a huge inter-pair skew. The key with the skew is because we are operating at high speeds and high bandwidth, high pixel clock frequencies, even a relatively small difference in the length of the two wire pairs will create a large amount of skew. So if we take our original signal and then we have the TMDS version, we invert it, and then we send it through the cable. At the other end, you can see that what was previously completely synchronized, with the transitions, now we've introduced this skew. And when we send the signal through the circuits to compare and reference them to each other, we encounter a problem called jitter. So the monitor needs to know when something is a high or a low, and effectively when we have jitter, there's no way of knowing whether it's a 1 or a 0. What it basically means is the transition between the 1 to the 0 cannot be predicted at what time it's going to happen. So what can we do to fix jitter? You need to use reclocking. However, let's take a bit more of a detailed look at jitter to help us understand it a bit. So let's imagine that we have a 3-bit sequence that can either be 1s or 0s. These are all the different possible combinations between all the different transitions. So if we take all of these transitions and we draw them on top of each other, imagine them playing through at the same time, we get this little figure here, which is what we can which can help us determine how good the signal is. If we look at it through an oscilloscope, this is what it looks like. So we've got millions of samples drawn on top of each other, and with a nice clean signal, you can see this is a nice clean pattern, and we call it an eye pattern because it can also close like an eye, which is what you want to avoid. So within the TMDS standard, there are important areas. If the signal is in the black area, that's okay. If the signal touches the blue area, we're going to see some problems, and that's kind of out of standard. But this signal looks okay because we've got nice clean lines and none of them are touching the blue area. And if we draw these two vertical lines in here, you can see that these are the ideal transition times. And you can see with this signal, all of those different possible transition combinations, all of them are happening at the through these lines, and so the timing is very precise, and this is a good signal. So where we might have some problems, well, if we take this ideal example again, we show the transitions happening, and yeah, they're all happening at the same time. However, if we have some jitter, what we might see is something like this, where the transitions are happening at different times. Some are happening before, some are happening at the ideal time, some are happening late. And so this is where the instability is. This is where we can't predict now where the transition time is going to happen. If we layer all these together, like we did for the previous clean example, and then we take the inverse and we layer that on top of each other as well, now you can see that we don't have these nice clean lines all happening at the same area on the ideal transition timeline. We have quite a fuzzy, messy area. And if we look at the example from the oscilloscope again, this is what it would look like. And you can see that there are samples being drawn on that blue area, and because of that, it's failing the compliance test. And so we can look at this and see that the sort of width of this particular area, we can measure that, and that's effectively what the jitter is. So in these scenarios, you need to use reclocking, which can make the timing of the signal of the transitions precise again. There's two different types of reclocking, TMDS and pixel accurate, and both can fix the problem. We'll look at that in a bit. However, there's another aspect where jitter can cause problems. So jitter has, it can also have a frequency. This instability, the shifting to the left and to the right, can be very slow or it can be very quick. And so we have high frequency jitter and low frequency jitter. So the HDMI standard says that jitter below 4 megahertz is called low frequency, and above 4 megahertz is high frequency. Each device and circuit that you have in your system adds a little bit of low frequency and a little bit of high frequency jitter. The problem is that the HDMI standard only cares about high frequency jitter. So HDMI was created for home applications where you have one direct connection from source to sink. You may add another device in between, but it's fairly simple. But when you send the signal through multiple different devices, low frequency jitter can accumulate. So we can show on this graph that after one hop, we have a small amount of low frequency jitter and virtually no high frequency jitter at all. However, we send it through different devices. And you can see by the time we get through the sixth hop, we've added in a lot of low frequency jitter. And because the HDMI standard says not to worry about it, none of the devices are trying to sort of eliminate this. And in this particular example, this could cause the signal to be unstable or not even usable. So getting back to intra-pair skew, where we started, this is how a signal might look. You can see that there's no idea where the transitions are happening. It's just a big mess. And this signal probably can't even be fixed with reclocking. Just going back to the eye pattern quickly, we looked at the ideal transition times, but you can see we also have these other blue areas, and these are relating to the amplitude and attenuation. So we can draw a line of, we had the ideal transition times. Well, this would be sort of the ideal sampling time when the device would try to measure whether it was the 1 or the 0. And we have the high area is nice and clean up there, and the low area is nice and clean over there. So this is our nice signal. If we then look at the sort of worst case scenario, you can see that not only do we have the jitter, but we also have a sort of wider area in these high and low voltage areas. And you can see that there's a sort of width to this as well. So it's not just that all of the voltages are a little bit lower. It's that some are a bit higher, some are medium, some are a bit lower, and this range is more of the problem. So in this example as well, this is where you would need to use equalization. Okay, I hope everyone's still following after jitter. I know it can be, that's one of the more technical aspects we will cover. Hope it all makes sense. But yeah, if you've got any questions, feel free to submit them. But moving on with interpair skew. So with intrapair skew, we had a difference in length between the two wire pairs, the two wires within one wire pair. And that was, for the same reason why it's difficult or impossible to get two wires to be exactly the same length in a wire pair. The same principle applies between two individual wire pairs. So if we start off with our blue and our green color channels, and they start off completely synchronized, once we send them through a cable which has a different length between these two channels, a different physical length, well, that ends up resulting in a skew in the timing, because it physically takes longer for the electrical signal to get through a longer wire. So what can we do to eliminate interpair skew? Again, reclocking is the magic word here. But the problem is, if you have too much interpair skew, then TMDS reclocking is not enough, and you need to use pixel accurate reclocking. So let's look at this interpair skew example and look at the reclocking. So here we can see, we can show the difference between TMDS reclocking and pixel accurate reclocking. So let's start with TMDS. Here we've got our 4 wire pairs that carry the red, green, blue, and the clock. And we send that through the cable. TMDS is a serial communication method, which means that the bits representing one pixel are transmitted one after another, like this. So we've got, within the red color channel for 1 pixel, we've got R0, 1, 2, 3, 4, all the way up to 9, giving us our 10 bits. And if we freeze time at this moment, and we have a look at the 2 neighboring pixels, well, the rising clock of our pixel clock, the rising edge of our pixel clock, that denotes when the beginning of a new pixel should happen. And with the blue channel, you can see that's completely in line. Just as the pixel clock is rising, the B0 bit information is being transmitted. However, with the green, we can see that green's running a little bit late, so it's still trying to get through the previous pixel, and the red channel's running a little bit early, so it's already transmitted R0 of that pixel. And if we were to use TMDS reclocking, what it would do is it would try to find the rising edge of these bits. So here we've got this, it can detect that we're part way through the G8 bit, and what it will do is it will skew that to the next rising edge. So from the TMDS reclocking point of view, that's the job done. We've reclocked everything to the nearest bit. However, you can see that we've still got a full 2 bits of skew going on here. So in this scenario, you might still have problems. The displays can accommodate for a certain number of bits being skewed, typically 1 or 2, but as you go through multiple devices and this skew adds up, you can very easily get into a situation where the signal can't be recovered. And if you do get to that situation, what you need to do is use another technology called pixel accurate reclocking. So this is a Lightware proprietary technology. And if we see the same example, and we take all of our pixels with the different color channels, and we have our pixel clock, what pixel accurate reclocking will do is it will take the whole signal apart, analyze it, and put it back together by taking the rising edge of the clock signal as the reference point. And this means that the outgoing signal is perfectly matched to the pixel clock signal. In essence, it's the same as if it came out of the source and is now prepared to go through multiple non-reclocking devices again. So the difference between the two reclocking technologies is the amount of skew that they can accommodate for. So TMDS reclocking only sees bits, doesn't see the pixels, and so it can only compensate for one bit of skew. So it's only recommended for relatively simple systems containing only a few hops. Pixel accurate reclocking can realign the pixels, so it's recommended for more complex installations. It's also worth mentioning TMDS reclocking is a more basic single chip solution, and pixel accurate reclocking is a slightly more expensive 2-chip solution. So most devices will have TMDS reclocking in them, but it's only with certain Lightware devices where pixel accurate reclocking is used to, as I said before, reconstruct the signal so that it's as clean as it was coming out of the source. So let's see what happens when you send a signal through multiple long cables and non-reclocking repeaters. So you may see noise, which is the flashing pixels, jaggies, the flashing horizontal lines, or even a complete loss of sync and an unstable picture. So all of these problems can be eliminated by pixel accurate reclocking. Great, that takes us on to our next topic, which is EDID, which stands for...
Sorry, Felix, sorry to barge in. Hi, I'm Tibor. I'm working in the background answering questions. Felix, do you think we can answer 1 or 2 questions, because they keep pouring in? So
yeah, let's do it.
All right, let me start one. So Randall is asking, does pixel accurate reclocking add any latency?
It doesn't add any notable latency. So it'll be on the order of nanoseconds. You won't be able to see, it's not something where you'll be able to see lines or even, it'll be a very, as with sending electrical signals through any medium, it takes a certain amount of time for it to go through, but it won't be, like with an AV over IP technology where you're adding frames of latency, or, it's not taking any extra processing time, let's say. So with pixel accurate clocking, latency is not something you need to consider.
Yeah. Okay, Bhavin is asking, while calculating the video bandwidth, do you need to consider the blanking interval in the calculations?
Yes. If we're talking about the bandwidth that you're sending through the cable, it's always important to think about the blanking interval. If you're talking about bandwidth you're sending through an IP stream, then that's a different thing. But in this context, talking about DVI and HDMI signals, which are only ever really present in transmission mediums, yes, you do need to consider the blanking interval.
Mm-hmm. All right, and one last question. Is the blanking area fixed value, or is it resolution dependent?
It depends on the resolution, and it also depends on the EDID, which is a nice tie-in. So the blanking interval will be defined by timing information that is present in the EDID.
Mm-hmm. All right, and one more question. We had multiple people asking, what exactly counts as a hop you say the signal hops?
So a hop would be if you've got an HDMI cable and it's coming out of an output port and then into an input port on a device, that would be one hop. And then if that device then has another output port and another input, let's say, that would be another hop. So effectively, I would consider it as the amount of HDMI or DVI sort of links you have in the system.
Yeah. All right, I think that's it. We had many more questions, but I would like to just assure everybody that we are going to answer all the questions either during this session or afterwards in a follow-up email, so you will not be left without an answer. But unfortunately, we have so much time for answering questions. So Felix, go ahead and talk about DVI.
Yeah. Hopefully, I think we'll have some time at the end to go through more questions. But let's continue with EDID. I say EDID. Some people say EDID. I guess it kind of depends where you're from, maybe. But what is EDID? We say that it's the passport of the display because it contains every piece of important information about the display, the manufacturer, the product type, data production, serial number. But the most important would be the supported resolutions and refresh rates. So why did we introduce EDID? Back when we were using VGA, you would have a situation where you'd buy a new VGA display for your machine and you'd plug it into your computer, and the picture was skewed off in the wrong place. So you had to dial in with the settings on the monitor to kind of move the picture into the right place and increase the size and get all of that set up correctly. Hopefully some of you guys can remember doing that. I certainly can. And that's fine if you just buy one display, but if you have a more complicated system where you're replacing displays often or you're breaking up and building down the system on a regular basis, every time you connect in a new display, you're going to have to do that configuration. So when we were designing a new video standard to replace VGA, that was one of the problems that the designers tried to resolve, and the way they did that was with this EDID. So the EDID is physically 128 bytes of data that is sent from the display to the source, and it contains all of the relevant information for DVI. But then when HDMI came around, they found that they added in a lot of new features, like with audio and other color spaces, and the original 128 bytes wasn't enough to contain all of that. So they added an extra optional 128 byte extension, the CEA extension, and anything that is supporting HDMI basically has this extension. So the full HDMI the full HDMI EDID is 256 bytes. And nowadays we also are entering the world of display ID, which will be another extension that is used to accommodate for even more stuff that no one envisioned back when HDMI first came out. The experiments we've been doing with it have been incorporating these ultra wide resolutions where the standard EDID doesn't give enough memory to even represent the larger number of pixels that you are using. With a standard EDID, once you get over 4096, it tends to break down. So to go beyond that, you need to go to display ID. So what happens when we connect a DVI source to a DVI display? We call it the basic handshaking. So the first thing that happens is the source sends a plus 5 volt signal to the display, which lets the display know that the source is ready, it's present, it's powered up. And sometimes this power on the plus 5 volt can even be used to supply voltage to the memory chip, which contains the EDID. So this way the source can read out the EDID even if the display is not plugged in. That's not the case every time, but it can be. And so when the display receives this plus 5 volt, it sends a hot plug back to the source, which is it can even just be the same 5 volt looped back. And this lets the source know that the display is also powered on and it's ready to receive. And this rising edge of the hot plug signal coming back is actually the trigger for the source device to start reading out the EDID. So the communication happens on this display data channel, which is why it's so important. And it reads out the EDID over this. If the source wants everything to be encrypted and use HTTP, then that will also happen at this stage. This is optional, and we'll cover HTTP in a later session. But then once these things have happened, then you can start sending the audio and the video over the TMDS lanes. So it's very important that the EDID must be read and sent for video to be transmitted. It's also something you can actually see happening with a laptop. The standard also says whilst the EDID is being read, you can't have your output turned on. So a lot of times what happens when you plug your laptop in to another display is the screen on your laptop goes black and then comes back again. And you can see that's when the EDID is being read. It can be quite a useful troubleshooting device because if you plug in your laptop and the screen doesn't go black, that means the EDID is not being read, which probably means one of these two physical handshaking signals, the power 5 volt or the hot plug, is not happening, which can even be diagnosed down to a broken pin on the video connector. So it's very useful it's a very useful way of testing your cable to see, okay, if I'm getting the EDID being read, then I know the cable, these handshaking pins are intact. We look at an example of an EDID. So here's the hexadecimal 128 bytes of raw data. We can translate this into more readable form. So the EDID structure has different fields. The first field is the header, and the first byte is all zeros. The next 6 bytes are all ones, and then the 8th byte is 0 again. It always has the same value, and it lets the source know that this is an EDID, and if you don't get this part, then something is wrong and it needs to try again. The next field is the manufacturer and product information. So this manufacturer is Gold Star Company, which is basically LG. And we have different fields for product code, serial number, all that stuff. The most important part of the EDID is the preferred timing mode, which is a detailed timing about the most likely signal to be displayed. This is usually the native resolution of the display. We say this is a detailed timing because it contains all the information about this particular resolution that the source needs to know. So it's not just the active resolution you can see here, but we've also got the horizontal blanking, vertical blanking, and effectively this is where the blanking interval is being determined. And also the parameters of the sync signals, whether it's H-sync polarity, V-sync polarity, different scan modes. So yeah, this is a detailed timing. And I emphasize that because, as we'll see, there are non-detailed timings. So this will be the preferred timing mode. There's also room for a second detailed timing. So in this case, it's normally for a lower resolution in case your source device can't display the original resolution. There's a backup resolution which is lower that is probably more compatible with more devices. And then in this next field, we can see that here we have the chromaticity and the established and standard timings. And so the standard timings are Visa standard resolutions, and they're non-detailed. They basically are codes that the source device can use to look up in its own internal memory and copy the timings defined by Visa. And on the last fields, we have the range limits descriptors, which contains the minimum and maximum frequencies for VSync and HSync, and the maximum pixel clock frequency. It's also got a product name, and the second to last byte is important. It's got the number of extensions. So in this case, that's 1, which means the CEA extension is also present. And then finally, we have the checksum. So with the CEA extension field, which we'll take a look at, it basically contains the stuff that is new with HDMI, so the new color spaces, new standard timings, short video descriptors for the new resolutions that were being used with HDMI, so that's the widescreen stuff, 16:9, and most importantly, the different audio formats. That's the real key new feature with DVI. Also room for additional detailed timing descriptors. So at the beginning, we have the support for the audio, the different versions of the YCBCR color space, and then we have our short video descriptors. So as you can see here, 1920x1080 is very common, and all the different refresh rates, and whether it's progressive scan or interlace. So this is all stuff that was new with HDMI. The field that's probably most interesting for people is the audio capabilities. We can see that this device supports 2-channel PCM, which is a high data rate, uncompressed, lossless format. There's different sampling frequencies and sample sizes that are supported, and 2-channel PCM is basically required as standard for HDMI audio. We've got a front left and a front right, so it's a 2-channel system. HDMI mode is supported, deep color mode is supported, deep color being the 30 and 36 bits per pixel, and the max TMDS clock is 225 megahertz. So if we, now that we know a little bit more about EDID, let's compare one of our Lightware factory EDIDs with the EDID from an average display. So the most important part, the preferred timing mode, is the same. We both have that resolution listed, 1920x1080. However, with the second detailed timing, the display has information, but the Lightware EDID is empty. Likewise for the established and standard timings. Then in the CEA, we also have 1920x1080 in there for the Lightware, but with the display, you can see there's a lot of different resolutions to choose from. So this is the key difference. With the Lightware EDID, with our factory EDID with only one resolution in it, this is something we can use to force the source device to use this resolution. The standard for DVI and HDMI says that you can only send a resolution that is listed in the EDID. Like with this display, there's many different options you can choose from, and depending on what source device you connect to it, it might decide to pick a different resolution. So there's a good chance you won't get a consistent experience with this kind of EDID. So even though EDIDs only have 256 bytes, they can create a lot of problems. So just because, and it's also worth noting, just because a device has certain details listed in its EDID, this doesn't actually translate necessarily to what the chips are capable of. So, you know, whilst the EDID might be a standard blanking size, if you send the chip behind it, the HDMI chip that's being used, a reduced blanking signal, it might still be able to process it. And likewise with all these other things. So just because the EDID might have a certain horizontal and vertical sync polarity, that doesn't mean that's the only configuration that the chip can support. It will depend on the manufacturer and how much effort they put into the EDIDs. Some manufacturers will just take one EDID and use it on a whole range of different products, which yes, can create problems. So as we saw before, both the basic original part of the EDID and the CEA extension can have resolutions supported in them. So with the basic EDID, typically these are VESA standard resolutions from you know, the DVI era, where we were using CRT monitors that were typically 4:3 or 16:10 aspect ratios. Then with the CEA HDMI era, 16:9 widescreen became the most commonly used aspect ratio, and you're more likely to find resolutions fitting that in the CEA extension. So it's not a hard and fast rule, but it's just a common practice. Any resolution can be supported in either part. But why is it important? Well, with different devices, they might read different parts of the EDID. So whilst some devices will read all parts of the EDID, you might get some early DVI source devices that hadn't been invented, or the CEA extension hadn't been invented when they were released, so they wouldn't even know to read the CEA extension. And you also get some HDMI sources that don't bother reading the basic EDID. It just goes straight to the CEA extension and might ignore what's in the basic EDID. So it's important to have, that's why with the Lightware factory EDID, in the CEA extension, we had the 1920x1080 resolution listed in that part as well, just in case you're using an HDMI source that might ignore the basic EDID. So moving on from this, we'll talk about EDID management. Now that we know a bit more about what the EDID is and what it does, let's look at some of the issues that might arise and some of the solutions we can have. So let's take an example of having a 1:4 DA, and in this kind of product, there are different approaches to EDID. So the first approach would be just to have a fixed EDID on the input device, and this EDID is fixed. It doesn't care about the capabilities of the display. So when we connect up our source device, it reads the EDID. It says, okay, I can send 1080p with deep color and PCM audio. And in this system, we've actually only got 2 devices that will support this signal. And our HD Ready TV and our DVI only display can't read the signal. And you can't do anything to fix this because the EDID is, you can't change it. Another approach would be to have the EDID be taken from a specific output, a kind of dynamic EDID management, where depending on what's connected to output 1, that EDID will be passed over to the source. So in this case, when we connect everything up, the same thing happens. It sees the full HD 1080p deep color supporting display on output 1, and we don't get pictures on our other 2 displays. However, in this case, we can actually do something to rectify this. If we switch the order of the displays and we put the HD Ready display onto output 1, now when we read the EDID, we'll have a signal which isn't deep color. So that will be backwards compatible with the HD Ready and the full HD display. However, the DVI only display, we won't get anything. And in fact, if we wanted to, we could put the DVI only display onto output 1, and we would probably get picture on all 3 displays, but then we wouldn't get any audio. So the AV receiver at the bottom there would be effectively useless. The third approach is sort of very complicated and is very hard to implement. Effectively, it'll read the EDID from all the connected outputs, do some processing to figure out what's the sort of lowest common denominator EDID, and then present that. So generate an EDID that represents the capabilities of all the connected devices. However, there's a lot of problems with this. It's very hard to implement. If you think about all of the millions and millions of different HDMI products out there and trying to come up with an algorithm that can incorporate the sort of lowest common denominator of all the different capabilities, it's very complicated. And again, the chances are you might present an EDID that doesn't get read properly or isn't able to work. And in that situation, what can you do? You don't have any control over this algorithm. So having looked at these different methods and approaches, let's look at the Lightware EDID management. So this is a standalone EDID manager product, but effectively the function of this product is built into most of the input ports on every Lightware device. So most Lightware devices have what we call advanced EDID management that we'll look at. So with this device, let's look at how we handle the EDID. We power on the device, and with these rotary switches, we can select between 50 factory default EDIDs, as well as some user memory slots where we can load in custom EDIDs, which we can load in either from learning from different devices or even connecting over USB and uploading it to the device. So let's say we choose our factory default 27 because we want to force a specific resolution. There's actually a guide on the back of the product which tells you which number corresponds to which resolution. So we've selected number 27 and we connect up our cable. This particular device has 40 dB equalization, so we can come in on a nice long 60 meter DVI cable. And we've got the source, the +5 volt. We send the EDID because we're sending the hot plug back, and we've got signal presence. So you can see even without the display being connected, we've got the source to start sending to start sending a signal. And this is why we call this EDID emulation. So what the EDID manager is doing is it's emulating a display. It's convincing the source device that a display is connected even when it's not. And when we want to connect the display device, everything's ready to go. We get the hot plug signal, we send the video along, and then we read the EDID from the display, and we save that in a specific memory location in case we want to use it later or edit it and do stuff like that. So EDID emulation is very useful for keeping your source signals active even when there's no display being connected. An example where this is used quite well is with like a watch out media server. With watch out, if the media server detects that the display is has been disconnected, it'll resize the active area and generally screw things up, and ultimately you'll need to restart the playback once you've connected everything. So the nice way to avoid this is to have every output from the media server connected to a device that has EDID emulation. If we take an example from this conference room, let's say we've got this nice new, what used to be a nice new projector, probably quite old now, and you've got 1920 by 1200 as the sort of native resolution, and you've set the screen size up and all of the settings for it to look great on 1920 by 1200. Well, let's say your partner comes in, he's using this Sony Vaio, and the desktop background of the display built into the Vaio is 1920 by 1080. So it's going to want to use that resolution, and it picks that option from what's available. Someone else comes in with this MacBook, and the built-in display resolution is different again. So it is 1440 by 900, and it's using up even less of the display, and you get this white border around, and you put lots of effort into making sure the viewing experience is optimum, but because everything's choosing a different resolution, you can't guarantee it. So the solution here is to put in EDID manager, which is supporting only the single 1920 by 1200 resolution. And now, no matter which device you come in and connect, you'll be getting the same resolution, and you get the same experience on the display. So here we have a quick summary about Lightware's advanced EDID management features. We have static emulation, dynamic emulation, EDID storing, editing, transfer from into and out of our devices, and custom EDID creation. So let's quickly go through all of these options. The first is static emulation. So let's see how this works. We've got 3 sources, 3 displays, and a matrix switcher, which is controlled by a laptop running our Lightware device controller. The CPU board of the matrix has factory default EDIDs and also user programmable slots, just like the EDID manager. And you can use a control PC to create or modify EDIDs and upload them into the user programmable slots. Static emulation means that the emulated EDID is taken from this internal memory of the matrix, so either from the factory list or the user memory. When the sources read out the EDIDs, they start sending their image, and the displays show them. So in this example, if we remove a display and we connect a new display, the image is displayed on the new display, and there's no issues because the EDID of that display is not actually being used by any of the source devices. How does this look in our Lightware device controller software? So when you connect to one of our matrices, you might see a page like this, and at the top you can see there's an EDID tab. When you connect on this tab, click on this tab, you'll see you've got a left and right, a source and destination. This is kind of regarding memory. So on your left, you've got your memory sources, and on your right, you've got your memory destinations. For sources, you've got the factory, user, dynamic, and emulated. And for destination, you've only got emulated and user. Emulated is the important one. That's what's actually present on the memory chip connected to each video input on the device. So that's what's actually on the video input. It's important to remember that EDID only travels in one direction, which is from the display device to the source device. So there's no way, EDID doesn't, you can't push EDID down the chain. It can only go in that one direction. So it's always important what to consider. It's always important to consider what EDID is present on the input connector. So on the left, you either select factory or user. In this case, we're going to go from the factory list, and let's select this EDID. And then on the right, let's select that input, and then we press the button and we pushed it across, and that's it. Now that EDID is emulated on that input. So static emulation is it's fairly straightforward. Let's look at dynamic emulation. So in this example, we're not emulating from the internal memory, we're emulating from a specific output. So whatever the EDID of whatever is connected to output 1, let's say we're emulating to all of our displays. However, if we do the same thing we did last time and we change the monitor, we get a new display, let's say, and we unplug it and we plug that one in. Now the matrix will detect that there's a new EDID in that location on that output 1, and it will then learned that, okay, we've got a new EDID here. That's what we're pushing to all of these displays. So now we need to read this new EDID, and that's where the output of all of the source devices gets turned off. Because as I mentioned earlier, when a new EDID is being read, the output has to be turned off. So in this case, by adding in this new monitor and by using dynamic emulation, we're going to lose the picture on all of our displays. It will then be propagated across, pushed in to the source devices, and then the signals will resume, but you will get that momentary loss of signal. So in this particular example, we wouldn't recommend dynamic EDID emulation. If you wanted to use the EDID of that particular display, you could always just save it into the user memory and then emulate it from there statically. However, there is a situation where dynamic EDID emulation can help quite a lot. Let's say we've got a more advanced system where it's not just a matrix switcher, but we're using some transmitters to extend the signal, and these transmitters are smart and they have their own EDID emulation capability. Well, if we use dynamic emulation on here, further up the signal chain towards the source device, we can push these EDIDs across, and let's say we want to then change the EDID. Rather than having to go into each transmitter and connect there, we can just change the EDID that is present on those inputs, and the dynamic emulation will automatically make sure that that EDID is then presented to the source devices. So this is an example of where dynamic emulation is a useful thing. So how do we store EDIDs? So let's say we go back to our software, go back to the EDID page, and on the left we take the dynamic page. So the dynamic page represents the output connectors on the device. So what's connected to output 1, 2, 3, and 4, reading the EDID from those devices. So if we select an EDID from here, and on the user list on the right, we can select the EDID from output 1 or monitor 1, and then save that into the user memory like this. And that gives us that EDID stored in the user memory, so we can statically emulate it if that's what we want to do. We can also edit EDIDs, but I would only recommend this for people who are professionals. I wouldn't let any sort of end users start playing around with it. The key is if you mess up the EDID and you connect a device to it, you can actually blue screen and crash that device. So every time, as long as you've got that HDMI connector in there, it's always going to crash. So just be a bit wary what you do with your EDIDs. But if you want to edit an EDID, you can select it on this left-hand page, click on edit, and it'll bring up our EDID editor. We'll go through all of the different EDIDs. So let's say one of the things you wanted to change was the preferred timing mode, and maybe reduce the blanking interval or change the refresh rate or pixel clock. You can manually do this. And let's say you've done that and you wanted to download the EDID. Well, uploading is pretty simple. You go to the user memory, click on an empty slot, and press upload. You can then find the file and access it from there. Likewise, to download, you just select the EDID and press the save button. And creating new EDIDs, we have an EDID wizard, creation wizard. So at the bottom, you can see this create button. You click on that, and you can select different resolutions from the sort of preferred resolutions, or you can even enter in a sort of custom resolution. This is quite useful if you're doing stuff with LED walls, LED wall controllers, where you've got an LED wall which is going to be a strange non-standard resolution. It's one of the advantages of the DVI and HDMI signal over SDI, where with SDI you can only choose from sort of standard broadcast resolutions. With DVI and HDMI, you can enter in custom resolutions into the EDID and get weird shapes and a bit more customization. So you type in the resolution and the refresh rate you want, and just click next, go through the wizard. Here we need to decide if we want DVI or HDMI. If we enable HDMI, then we have to say something about the preferred audio settings as part of the standard. Let's say we want to do just a basic PCM. And then at the end, we can give it a different name, so something that might be a bit more useful. And we can save it as a file, but we can also upload it directly to the user memory. So that's an overview of the advanced EDID management of Lightware devices. Hopefully that's clear, and yeah, you've got any EDID can be quite a confusing subject a lot of the time, so if you've got any questions, feel free to put them through. We've got half an hour left, so let's go through. Oh, sorry, Tibor.
Can we just answer one question?
Yeah.
Urman is asking whether EDID is used for both analog and digital video signal transmission.
There are analog EDIDs. So if you have a VGA output, let's say, you can find that some VGA cables are missing the pins for the DDC channel, and if you plug that that device in, let's say you're plugging a display into your laptop, you might see that display as a generic P&P monitor. That's normally an indicator that the DDC pins aren't there, or there's no EDID being read. So you can send a VGA signal without an EDID, so you don't need it. But if you do have a VGA cable with those pins on pretty much all devices that you're going to be working with nowadays, there'll be an analog EDID. And yeah, when you check the settings on your computer, you'll see that display come up with a name, you know, from the EDID. So if it's an LG monitor, it'll be LG whatever. So it's not required. But
yeah, you have these Y cables, these breakout cables. You have DVI on one end, and then it breaks out to DVI-D and then the VGA. In those cases, the DDC is usually connected to the DVI side, so it's not connected to the VGA.
Yeah.
In some cases, it is connected, but if you connect two sources, then they can mess up the communication because three devices are trying to communicate, and that's not.
Yeah. No, that's so yeah, it can be, but it doesn't need to be, basically.
Yeah. All right. Carry on.
Let's go through the HDMI side of things. So HDMI stands for High Definition Multimedia Interface. Hopefully you guys will have seen this connector before. This is the sort of commonly used Type A connector, and you started to see these around 2002. So we look at the evolution of HDMI and the available bandwidth. So with actually the first version of DVI is actually of HDMI is actually DVI. It's an evolution from DVI. They use the same TMDS architecture. They communicate over DDC. If you look at the pinout, it's very similar. And the bandwidth for HDMI 1.0 up to 1.2 was fixed at the same as DVI. So this allowed the maximum resolution of 1920 by 1200, or most commonly 1080p at 60 Hertz. Then we had HDMI 1.3. The standard actually defined a maximum of 10.2 gigabits, but in reality, most chips only supported 6.75 because that was the speed required to implement the new feature that was introduced with HDMI 1.3, which was deep color, which we'll look at. But it basically means using more bits per pixel. Then with HDMI 1.4, sorry, we got to true 10.2 gigabit support, and that allowed us to get up to 4K 30 Hertz signals, or even 4K 60 Hertz if we used a common subsampling method, which we'll talk about in the second part of this tomorrow. And then now with HDMI 2.0, we finally got the true 4K 60 444 support, because the bandwidth required for that was up to 18 gigabits. We can look at the evolution of HDMI from a different point of view. So just looking at the features that were added. So first we had DVI, there was no audio, it was only RGB, and it was all 8 bits per color, so 24 bits per pixel. Then HDMI 1.0 was released, and we added in these audio formats, so PCM, Dolby, and DTS. And then we also added the new color space, YCBCR, and YCBCR had 2 subsampling methods, so 444 and 422. We also added in the CEC, the Consumer Electronic Control, so that was an actual extra wire in the HDMI connector, and that allowed you to, in the beginning it was basically if you bought a Samsung display and a Samsung Blu-ray player, when you turn on the Blu-ray player, it will turn on the display, that kind of stuff. And so then we had a couple of versions with 1.1, 1.2, basically adding new audio formats. I remember a Super Audio CD at the time was a big deal, but now no one talks about that. And then with HDMI 1.3, the next big step was supporting lossless audio formats, Dolby True HD, DTS HD, and then also deep color. Then with 1.4, we had some cool new features with support for 3D, ARC, which is the audio return channel, and an embedded HDMI Ethernet channel. It also defined an automotive connector, which was more secure, but only really see in the car industry. And then with HDMI 2.0, that's more or less where we are now. It has 18 gigabits, so we could do the 4K 60 444. It also has YCBCR 420, so a new subsampling method, or a new sampling method, sorry, it's not subsampling, for YCBCR, and then Rec 2020, which is a new color space, and then more support for more audio channels and streams. And then there's been a couple new versions or new subversions which were supporting new HDR formats. And HDR is a very interesting topic at the moment, and that will be covered in part 2 of this. But going through HDMI, all of these are backwards compatible back to DVI. So if you had an old DVI computer from the 90s and you plugged it into your new HDMI 2.0 display, you'd be able to get a picture. Likewise, if you had a new HDMI 2.0 sort of graphics card and you plugged it into an old DVI CRT monitor, you'd be able to get a picture. It's important to say that DVI cables can carry HDMI signals with audio. So it's worth making a distinction here between the HDMI and DVI connectors and the HDMI and DVI signals. So you can send an HDMI signal over a DVI connector because they share, because they're backwards compatible and they share a lot of the same things with the 4 TMDS lanes, the DDC channel, the plus 5 volt, and the hot plugs. The connectors themselves are actually very similar, whereas the signal types have some key differences. So one of the key differences between the HDMI and DVI signals is that now in the blanking interval, we're not just keeping it mostly empty and just having the VSync and HSync signals. Now we're putting actual useful data in there. So we have the info frames and the actual audio data. So this is why we don't need a special cable to transmit the audio. The audio is actually embedded into the blanking interval in line with the video signal. And as I mentioned before, we've got a new color space, so it's not just RGB, but we also have YCBCR. So if we talk about the info frames, it's with each full frame, you're sending one info frame. And why do we need info frames? Well, with DVI, it was more simple. The display device knew what the signal was going to be. It was going to be an RGB signal. But now, because we've got different color spaces, we need to be able to tell the display device about the incoming signal. So with DVI, we had communication from the display going to the source device through the EDID. Now with HDMI, we also have information from the source going to the display about the incoming signal. So with the AVI info frames, that's the color space. We also have the pixel repetition factor, which is a feature that becomes enabled when you're sending very, very low bandwidths. So it's not something that typically gets used. It's where the pixel clock frequency might be lower than 25 megahertz. We also have the audio info frame. This will talk about what audio codecs being used, how many channels, front left, front right, all that kind of stuff. And so one of the big differences is DVI receiver chips can't handle info frames. If you send info frames to most DVI receiver chips, it'll freak out. Now, having said that, you might get some products that are labeled as DVI but actually can support HDMI signals with info frames. So for instance, with Lightware, we have our older 16x16 DVI matrix actually had an HDMI chip inside it and could process HDMI signals and info frames. The only thing it couldn't do was handle HDCP, which is a necessary part of HDMI. So that's why we couldn't advertise it as an HDMI product, but it wasn't really a DVI product as well. So it's important to know the DVI chips can't handle the info frames, but what chip is inside what product is kind of a different story. So let's talk about the color spaces. We have this colored image of a forest, lakes and mountains, nice and colorful. There's two ways we can represent this. As we've seen before, we could have the red, green and blue color components and strip them out, and when we combine them together, we get the original image back. Or we can do it in another format, which is YCBCR. YCBCR was first came into use around when color TV was developed. So when color TV came around, they wanted to be able to transmit a format that if you had a black and white TV, you could still get your Y component, the brightness, and see the black and white image. But if you had a newer display which could handle the CB and CR, the chromaticity channels, you would then be able to combine that and get your color picture. So Y is luma, and CB is a chromaticity component. It's blue minus the luma, and then likewise CR is also chromaticity. It's red minus luma. So when we start talking about YCBCR, it's important to go back again, and this is another area where we have one of our tricks, our illusions. So if we look at the eye, and we want to understand why YCBCR can be better sometimes, we need to think about how the eye works. So if we look inside the eye, as I mentioned at the beginning, we have different cells. Some are sensitive to the red, green, and blue color information. And then we also have cells which are sensitive to brightness information. So the cells that are sensitive to color are called cones, and the cells that are sensitive to brightness are called rods. It's important to know that the cones themselves are only focused or only present on a very small part of your retina, sort of near where the center of your vision is. So where you're focusing, where the sort of central part of what you're looking at, that's where you can actually see color information. And all the color around in your peripheral vision is actually sort of being processed by your brain and putting it in there. But the key here is with the cones and the rods, there's a lot more rods than there are cones. So sensitivity to brightness information is a lot greater than it is to color information. Or we could say that the resolution of our eye is much higher for brightness than it is for color. So here I have some examples of where you might see this. You know, during the day and it's bright, you can see color information very well. But if the sun goes down and it's a very poorly lit atmosphere, then you may not be able to see color very well. So we can take advantage of this in video signals and degrade the color information and send less color information than we send with brightness information, but not necessarily have a noticeable loss in quality. I have a couple more examples of just to illustrate how your color vision works a little bit. So here we have this image, and you know, when we look at it at a glance, we can see that there's color in it. But if we zoom in on it, you can see that the color in the image is only represented on a very small grid, and that most of the image is actually black and white. But our brains are so good at processing that we are able to sort of, you know, see the color in the shirts on these people. Here we have a bit of an optical illusion. So with this one, if you stare at the dot and we see the image, it'll change, and you'll notice that when it changes, you can see the color. But if you move your eyes away from the dot, you'll notice that the changed image is actually in black and white. And this goes back to what I was mentioning before, that only the central part of your image of your vision can actually see color information. So when you're staring at the dot and the image changes, the color that you see in the image, your brain is kind of putting that in there. But as soon as you move your eyes and you actually start to get color information from that part of the image, it quickly changes to black and white. This is something I've done in some of the in-person trainings. I don't know if it translates so well over the webinar, but yeah, just is a good example of one of the many sort of tricks and illusions that come together in our brains to give us the illusion of a full color image and full color vision wherever we're looking. And it also ties into the YCBCR sampling methods. So we have different methods, 444, 422, 420, and the difference between them, well, with each of them in the Luma, the Y, we have each pixel has its own information. And with 444 and the chromaticity information, you can see that each pixel has its own information. However, if we go to 422, we can see that two neighboring pixels are sharing the same chromaticity information. And going down to 420, that's where we have the 4 neighboring pixels sharing the same information. And 411 is the same, just in a different format. So 422 is widely regarded as visually lossless. It's used in the broadcast industry and is a sort of professional level of subsampling. And yes, by reducing the amount of color information that we're sending, we can actually reduce the bandwidth of the signal we're using, but still keep the same quality video signal. So when you're using YCBCR and you're mixing between HDMI and DVI devices, you might sometimes see an issue like this, which is where the DVI display might have a weird color on it. Now you might think there's something wrong with the color channels, but actually everything's being transmitted correctly. It's just that the DVI monitor is trying to interpret the incoming signal as an RGB signal, but in fact it's only YCVCR. So this is a color space problem. What you could do to resolve this is if you edited the EDID being presented to the source device and disabled YCVCR support for it, because everything's backwards compatible with DVI and RGB, you would be able to get it to send an RGB version of this signal. So with HDMI 1.3, we had deep color. So let's look at where we might see deep color. If we have an image like this where we've got the sky and we've got a transition between a sort of light blue to a darker blue, and it's going across, let's say this is a 1920 by 1080 image. Well, that in this example, we'd have 1080 lines vertically to transition between the light blue and the dark blue. But with 8 bits of color, we only have 256 different shades, and that's from full black to full blue. So the number of shades that we have available to us doesn't match up with the size of the display that we have. And what happens is we'll have neighboring lines sharing the same shades, and it creates this banding effect. So in order to resolve this, what can we do? Well, we can use more bits per color. So going from 8 bits to 10 bits, 10 bits, you would be hard pressed to be able to see the difference. I mean, if you're close to the display and looking at a static image, you might be able to see the difference. With 12 bits, you won't be able to. It's physically impossible. So what that means is that we end up having to push more bits through our cable. So let's say we had 30 bits per pixel, that's 8-bit color with the 2 bits from the TMDS encoding. 12-bit or 10-bit color gives us 36 bits per pixel, and then 12 bits is 48. So even with the 10-bit per color, by increasing the bits per pixel, because we're using binary numbers, it will increase logarithmically. So we go from having 16.7 million colors with 8 bits up to 68 billion with a 10-bit. So that's more, easily enough for most applications. However, by increasing the bits per pixel, now our TMDS clock frequency comes out of sync with our pixel clock frequency. So previously with 1920 by 1080, we had a pixel clock of 148.5 megahertz, and with 8-bit color, the TMDS clock would be the same thing. But now with more bit depth, the TMDS clock has increased to 223 megahertz. So taking a look at HDMI 1.4, we got some nice improvements with the bandwidth, but we've also got the Ethernet channel and the audio return channel with 3D support. So if we look at the HDMI cable itself, what's changed since 1.3? Well, the TMDS lanes are still the same. The DDC channel is the same. The power 5 volt is the same. The CEC is the same. But now with the hot plug, we have another purpose. We are using it to send HDMI, Ethernet, and audio return channel information back from the display to the source. And then we had a reserved wire that was not being used, and now this is being used to send forward information to the display. So HDMI Ethernet packets from the source to the display. And in the newer cables that came out with HDMI 1.4, this hot plug and reserve wire were actually twisted together to make a twisted pair. And at that time, they released some new sort of logos to sell these cables. So HDMI has a rule where you can't advertise the version number to sell the cable. You can only sell it with the features. So that's why we had HDMI high speed with Ethernet, HDMI standard with Ethernet, and then now with HDMI 2.0, once again, to reach the higher bandwidths, you need new cables, which have a sort of premium certified logo on them. So we just take a quick look at the audio return channel. If we have this scenario with our Blu-ray player, it's sending HDMI to the AV receiver. That takes the 5.1 audio out to your nice sound system, which you want to use because your display only has crappy 2.0 speakers, and that's fine. However, more and more nowadays, the display itself will be the source, whether it's Netflix or some sort of Freeview. And in this scenario, if you wanted to be able to play audio out to your nice sound system, you'd need a secondary audio cable, normally a Toslink or optical cable. What the audio return channel does is it allows you to send this backwards channel of audio data through the HDMI cable itself. So basically, we're saving ourselves that extra cable, which in a home environment can be convenient, but in a professional environment could represent a lot of less, that many fewer cables. With HDMI 1.4 Ethernet, it's a very similar thing. Previously, you had to connect all of your devices to the network to get the benefit of having them online. Now, with cables that have an Ethernet channel in them, we only need to connect this one device, and the display can act as a hub for the rest of the connected devices. So the newest version of HDMI is 2.0. The most notable change is the maximum bandwidth, which is 18 gigabits, which supports true 4K 60 444. It also supports the new subsampling 420, although technically you did see that on some HDMI 1.4 devices, which we'll go over tomorrow when we talk about 4K. We've got the Rec 2020 color space and more audio support, and also the new sort of ultra wide 21:9 aspect ratio. So I think that's where we're going to end it for today in terms of the presentation. So if there are some questions that we can go through, yeah, happy to do that.
Yeah, I'm back.
Great.
So Daniel is asking, isn't 444 the same as RGB? Thought 444 does not make use of YCB and CR.
You can have YCB-CR 444 as well. So you can have RGB and YCB-CR sampled at that same sort of data level, and they should be equivalent in terms of quality. YCB-CR typically gets used more with the 422, and if you were going to be sending 444, you're not going to save any bandwidth, so there's no benefit to using YCB-CR. You could use RGB and get the same quality at the end.
Yeah. All right. How to handle EDID when dealing with SDI or 3G SDI signals?
I don't have as much experience with SDI, but from my understanding with SDI, you kind of set your source and your display device to a pre-configured broadcast standard, and it interprets the signal that way. So in that sense, the source device isn't actually reading anything about the capabilities of the display device. You have to manually set that. And use the sort of SMPTE standards, which can be a drawback, but I guess it can also be one of the strengths because the standards are very tightly defined, and you should know exactly what you're going to receive at the other end.
Yeah, SDI is bulletproof. HDMI and DVI are flexible.
Yeah, that's a good way of putting it.
All right. One more question. While using EDID management in Lightware, if you're using the factory EDID, and in case the source does not have support for that resolution, what will happen?
A lot of times it will revert back to something like 640 by 480. I've seen happen. So the lowest possible resolution it can use. That's the most common thing I've seen. You might expect it to not send anything, but that seems to be a kind of fallback, particularly for laptops and those kind of devices. If you were using it with a Blu-ray player, you probably wouldn't see anything.
Yeah. All right, quickly. Is 4K 6420 possible with HDMI 1.4 or not?
Yes, it is. So when HDMI 1.4 came out, they kind of picked out this upcoming feature from HDMI 2.0 and implemented it early. So it was, in terms of the standard, it was defined in HDMI 2.0, but in terms of practice, it started being used before HDMI 2.0 devices were on the market. So HDMI 1.4 devices and also HDBase-T can handle the 4K 60 420 signal.
All right, our time is up, so I just want to assure everybody that we are going to answer all the questions in a follow-up email. And yes, the recording, there will be a link to the recording of this event in the follow-up email, so you can watch it later, or if you missed something, then you can go back and watch that part again.
Yeah, I just want to say thanks for all of you for joining, and I hope you found it useful and interesting. So we'll be carrying on tomorrow with part 2, and then on Friday with the part 3. But yeah, if you have any other questions or anything like that, you can always send an email. My email address is felix.knight@lightware.com. Or you can hit up the support channel. But yeah, thanks everyone for watching, and yeah, hopefully we'll see some of you tomorrow. Okay, bye everyone. Okay.